Well, hello everybody, and welcome to another live virtual office hour here on the Weather West channel. I'm Daniel Swain, for anybody who's joining for the first time. I know there are a few of you today, so welcome. And just a reminder that this channel is partly sponsored by Reask, a climate tech company that is helping other organizations rethink their extreme weather exposure in a warming climate. So today I want to talk about actually two quite distinct things. First, the upcoming period of strong winds in California, particularly in Southern California, where there will be a major Santa Ana wind event later this week with very high fire risk. Talk a little bit about why, while the same windy conditions in Northern California probably won't produce the same level of fire risk up north. And then I also want to switch gear and talk a little bit about what happened in Spain. I would say last week, but actually this is an ongoing event with flooding continuing up to the moment right now. There's actually been a renewed wave of very heavy precipitation and flooding there. So, as has often been the case in recent months, I want to talk about something that's going on closer to home in the West, and then also about the broader context of a major extreme weather episode that has unfolded with pretty catastrophic effects globally. Also wanted to draw folks' attention to a couple of links that I posted in the chat. You can click on them at your leisure. But the first is a link to a new and free documentary film on YouTube about climate and Earth system dynamics, including tipping points on a warming world. That's a film that I was involved with. Strongly encourage folks to check it out if you have a moment. I think if you've showed up to this channel to listen to me speak, you'll likely get something out of it. So please watch it and share it with your friends and family as well. And the other link is a link back to my previous office hours in case you missed that one. A lot of folks said that they didn't realize I was going to be having this conversation, so in case you missed it, it's all recorded. The original live discussion is archived, as are all of these sessions, regarding the election and its implication for weather and climate prediction and studies in the U.S., and in particular, I talk a lot about what the role of the National Weather Service is and how it's quite different and arguably unique in the United States relative to essentially every other country on Earth, and why my personal and professional view is that it would be a real travesty for it to be severely diminished. So feel free to check that out via the link. And with that, I'll move on to the weather. So, as many folks may have noticed, it's pretty windy out there yesterday if you're in Northern California, or today in Southern California, and that is going to be the beginning of an episodically quite windy pattern to come for the next week or so at least. And the strongest of the wind events to come actually looks like it's not going to come until Wednesday or Thursday of this week, and be particularly focused in Southern California, although it will be windy again up in Northern California. At this point in the season, the main concern, of course, is elevated wildfire risk during strong wind events. But there is an important consideration here, which is that not all strong wind events produce extremely high wildfire risk, because, of course, the antecedent conditions that led up to this moment matter quite a bit as well. And by that, I mainly mean how dry the vegetation is leading up to a strong wind event. So you can imagine, for example, a midwinter strong offshore wind event following a major 2 or 3 inch rainstorm has very close to zero fire risk. In those settings, you might not be able to light a match to outdoor firewood if you tried. But if that very same wind event occurred following, say, a summer of record-breaking heat without a significant amount of precipitation preceding it, then that might be an entirely different story. And right now in California, we're at an interesting juncture where the conditions are very different in the northern third and the southern two-thirds of the state. So in the northern third of California, I think this week will essentially be a non-event. Fire weather-wise, the risk is never zero when conditions are relatively wet, but it's very dry and windy in the short term. But I don't think this is a particularly high-risk situation for most of Northern California, not because it won't be dry and windy, but because the vegetation has benefited from a couple of weeks of wetting to significant precipitation. So most of the northern third of California, really north of about the Interstate 80 corridor, is a pretty rough guide, has seen in the last couple of weeks at least a half an inch of rain. Some places have seen more than that. That's really going to tamp things down up north. So even though it'll be windy, even though relative humidity will be low, even though the vegetation will dry out considerably, and there may still be some grass fires, I don't think this is not one of those events that makes your hair stand on end, if you will, for the northern third of the state. It's a little bit of a different story, though, as you go south into, especially in Southern California, from about the transverse ranges southward. So that does include much of the central coast, too. So San Luis Obispo, Santa Barbara, Ventura counties, and really everything about south and east of there. There has been some brief precipitation recently, but in most cases we're talking about a few hundredths of an inch, maybe a tenth of an inch. That is not even enough to get the ground wet under tree canopies in most cases, for example. So with one day of dry and windy conditions, all of that water is gone. And then with multiple days of dry and windy conditions, as we're going to see down south, you actually end up even drier than you were before. So I think we're going to see a tale of two different fire risk zones in California, where Northern California, and by that I mean really north of about Interstate 80, pretty low risk from this event. Not zero, it'll be dry and windy, but vegetation is not super dry. South of that point, the situation is a bit different. There is a bit of a gray zone in the southern Sierra and portions of the central and southern Bay Area, where there are, in some of those cases, red flag warnings in effect right now. And I think that in some cases these are kind of marginal, because I don't think the vegetation moisture is necessarily dry enough to really support extreme rates of fire spread right now, even if it's very windy in a lot of those places. But the problem is the rain in recent weeks has been quite patchy in those places. So some places have seen a quarter inch or even close to a half of an inch of rain in the Bay Area over the past couple of weeks, but other spots are essentially at zero. And so that results in a patchwork of vegetation dryness across the landscape. So there's this patchwork in the Bay Area and the central southern Sierra where things mostly aren't extremely dry, but locally they're drier than elsewhere. But in some places there's been enough precipitation that the risk is pretty low. As this week drags on and no additional precipitation falls and we get the very low humidity and stronger winds blowing for days on end, the risk will probably increase a little bit, and I think that's the main reason why the red flag warning is in effect. Although again, I think it's a very different situation in the Bay Area and the southern Sierra than it is, say, in the transverse ranges of Southern California or even in the coastal zones. So thinking about the mountains in LA County and Ventura County and really the rest of Southern California down to San Diego County, those places are going to be at very high risk of fast-spreading wildfires during this event because there is not the legacy of recent significant rainfall. Vegetation is, if not at the seasonal peak, it's not that far below it, and it will dry out further this week with the atmospheric blow dryer, if you will, of these dry winds. At least it won't be particularly hot. This is technically a cold Santa Ana event, actually, although it won't be all that cold on the coast because the air mass to the east is cold, but then you still get that compressional warming as that air descends from the desert plateaus westward, and so it warms in so doing. And so you kind of counterbalance the cold air mass to begin with the active warming of that air mass as it dries and compresses, sinking down towards the coast in those strong gusts. So it will be temperatures maybe close to average in coastal Southern California, cooler than average in the deserts, classic cool Santa Ana event. But the more important thing, of course, for fire risk at this point is not the temperature, but it is the dry vegetation and very strong winds, very low humidity that are likely during what it looks by all indications to be quite a strong Santa Ana wind event in Southern California by Wednesday or Thursday. So that will be a very high risk event, high-end fire weather event for Southern California. Now, what's interesting is that the PG&E, the electrical utility in Northern California, has stated that they are planning to shut off the power preemptively. These, of course, are known as public safety power shutoffs, the PSPSs, if you will, the acronym. And Frankly, I'm a little bit surprised that's the case. It's possible they don't end up actually implementing the outages, because we've seen this before where they say they might do them and then they ultimately don't because certain trigger points are not met. In this case, the trigger points I think might not be met would be the vegetation moisture, which is not extremely dry. And as we all know, that ends up being a really important determining factor. The last big wind event in Northern California, for example, the vegetation moisture started out at a significantly drier place than it is right now. So I don't think there's the same level of risk up there. Contrarily, in Southern California, the risk of this event is a lot higher. And we haven't seen major wind-driven fires yet this year in Southern California. We've certainly seen some terrain and plume-dominated fire behavior back during that big extreme heat wave in September. The bridge fire, the airport fire, the line fire, two of which are still smoldering, in fact, and there may be some smoke production from those fires during this wind event, hopefully within containment lines. But this will be an event that we haven't seen. Now, is it unusual to see this in November in Southern California? Not really, especially it's early November. This is still a time of year where it's often still dry in Southern California, and when offshore winds tend to like to occur. But again, we are on the heels of what across inland parts of Southern California was a record hot summer, not so much for the coast, but then September was a record hot month for the coast. And so now pretty much everywhere in Southern California that has vegetation available to burn has experienced at least one record-breaking temperature month this warm season and has not yet received widespread significant precipitation. So that is the backdrop for this strong wind event, this strong Santa Ana wind event later this week, where in Southern California, the risk will be very high for fast-spreading and potentially dangerous wildfires. From the Bay Area northward, not so much. And that's not because it won't be windy, but it's because the vegetation is simply not as dry. So this is why, by the way, it's so important to know exactly when the first soaking rain of the season occurs, even though most of Northern California is actually running behind seasonal totals. So most of Northern California still has below average precipitation totals for the season to date. Granted, that doesn't mean all that much through early November. It's kind of noisy. But because there's been at least one and maybe two soaking rain events in a lot of places, even though the total amount is still below average, that helps a lot from a wildfire perspective versus zero. So in this early season, the timing of that rain matters in some ways more than the amount for wildfire purposes. Now, if you're only getting a couple hundredths of an inch, that doesn't really count. But once you're up into half-inch territory and you get a couple of events like that, even if you get only two and you normally would have had four by this time of year, you're still in pretty good shape, generally speaking, from a fire risk perspective. So, I would never say never, but right now I don't think it's likely to be a super high risk event for the Bay Area, for the I-80 corridor. Very different story for the Central Coast and coastal Southern California, where I think it will be a big deal event, and we may see some pretty problematic fires break out later this week, particularly on Wednesday and Thursday. There is, by the way, a preceding Santa Ana wind event occurring right now, and the fire risk is elevated in Southern California right now, but it's not nearly as high as it will be later this week, partly because later this week winds will be even stronger and relative humidity will be even lower, but also because right now the event is doing some of the pre-work for the second risk event, which is to say it's actively drying the landscape out right now. It isn't yet at critically dry levels, but it very likely will be by Wednesday or Thursday, so that's the concern there. So I think it might make sense for me to bring up some imagery on screen. So you're going to see my screen, and I'll be sharing momentarily. So you'll see that infinite mirror for a moment. Now what you're going to see is, I don't want the night mode here. Let's get rid of it. Okay. So here's where we are right now. Again, this is the European model ensemble. If I have to pick one, this is typically the one that I pick. And let me just verify that you're seeing what I'm seeing here. Yep, you are. I'm going to bring my drawing tool up again. Hopefully folks see it. And there's always some issues with that, but we'll see if it works this time. Not the end of the world if it doesn't. So this is sort of I guess this was earlier today, so let me advance this forward to present time. So here we are today, essentially yesterday into today. You can see this is known as an inside slider low pressure system, because essentially what it's done is the inside slider takes a trajectory like this. So what we've got is a low pressure system that, instead of coming down the California coast like this, which would be a wetter pattern, because then you have flow like this onto the state from the ocean, or on the low pressure, you get moist air moving upslope and you get rain in California. Instead, with this inside slider trajectory here, this is mostly dry for California, but can result in significant wind activity. So what you tend to see classically in the wake of an inside slider system is it's not the initial passage of the low pressure system itself that initially results in big time winds, but it is instead what happens afterwards. So you see the low pressure move through, and then if we switch over to temperatures, what we can see is we essentially went from conditions that were near average across the Great Basin. So thinking again about this region in here being the critical zone of importance in this context. This is over the weekend temperatures being near average, but as this low pressure system comes through, it gets much colder over the Great Basin specifically. So here we are right now. There's a bunch of cold air at the surface over the Great Basin, and then we see that pressure gradient set up. So the cold air that comes in the wake of it, that results in typically a surface high pressure system. So remember, cold air is more dense. So that's what we're seeing right now over the Great Basin. So you can see that the upper levels, the low is down here, but behind it, surface high pressure builds in. And that means that we tend to see winds, because of the surface high pressure from that cold air, we tend to see offshore winds, or at least sort of north to south winds like this, that develop as a result, because there's relatively lower pressure along the California coast, higher pressure here. That's the surface pressure gradient we see. And that's what we saw with today's more moderate winds, yesterday's winds in Northern California. But as we go through the week, this is what we will see. And I actually may switch over to just the non-ensemble, just the usual, the specific deterministic European model itself, just for illustrative purposes. But going back, or actually I should say going forward in time, here's where we are right now. That low pressure system moves away. We get quiet weather for a couple of days. But now, what do we have? We have a new inside slider. But this one is I guess I'll call it a deep inside slider, in the sense that instead of taking this trajectory just inland of the coast like the last one, this one's going to be dropping down way to the east. In fact, it's even going to be dropping down way to the east and then coming a little bit back west, like this. So you'll see that as I step this animation forward in time. This is why this is going to be mainly a Southern California wind event. So as you can see, the upper level low is centered right over, actually not far from the Four Corners region. So we have surface flow in this direction around the low, but what we're going to see is we're going to have those strong offshore winds, because at the surface, even though we have low pressure here aloft, what you're going to see, and by the way, this is a test of my meteorological knowledge in real time, because I haven't actually looked at what the data shows yet. I'm just guessing that based on the basic force balances and thermodynamics of the atmosphere, what we will see is development of high pressure near the surface in the wake of this low pressure again. So yep, this is what we see. What's interesting here, and this is why I think it's enlightening to step through this, what you see along the crest of the topography in California, what you're seeing here is let me get that to stay, that line here. This is essentially an outline of the places that are at lower elevations versus higher elevations. So if you're in Southern California, this is roughly the crest of the mountains. East of here, you're in the high desert, essentially. And east of here, you're in the Great Basin. So you're up in the eastern side of the Sierra. And you can kind of tell, if you look at a topographic map, this is kind of how the topography in California is aligned. It represents a barrier to air masses. And what's happening during an event like this, a strong Santa Ana event, is you've got essentially, let me get rid of that, you've essentially got a very strong pressure gradient. So look, anomalously high pressure over the high desert where it's going to be cold. So again, surface high pressure and cold air are usually associated because cold air at the surface is dense, but not high pressure along the immediate Southern California coast. In fact, if you go offshore, you actually have unusually low pressure. So if you were to draw a line from the high desert here to, say, some point 100 miles or so off the coast of California, and you just draw this dashed line here, what you'd get is a strong offshore pointing pressure gradient. This is going to drive surface winds in this direction. And because, as I mentioned, there's this boundary in the topography going like this, as that air moves in that direction perpendicular to the topography, it's moving downslope. So it's moving, air is literally blowing downhill. And as pressure increases, as you go lower in elevation, that wind, as it's descending the mountains, is compressing, and it's warming, it's drying, and it's intensifying. So again, this is another lesson in meteorology. I haven't looked at the data. So far, so good with the high pressure and the low pressure in the expected areas. Temperatures over the high desert should be pretty darn cool. There we go. So it's cool over the high desert and not so cool along the coast. So again, looking at the exact temperature, this is exactly what you'd expect to see with the temperature distribution right along this line, colder than average in the mountains and deserts, but even slightly warmer than average right along the immediate coast. So a very strong thermal gradient. What I'm going to suggest is that we're going to see strong winds pointing in the direction expected. Now, this is the final piece to pull this all together. And what we indeed see, and I wish we could zoom in. In fact, I actually can zoom in a little bit here, is what we see, and I'm going to try and find the right variable to illustrate this here. Yeah, this is probably a good one. So when you look at a wind map, you look at the direction, these are called wind barbs, and what you essentially, the barb is pointed in the direction that the wind is blowing to. So in this case, for example, if you zoom in on that particular wind barb, what you see is an arrow pointing to the southwest. So you do in fact see winds over Southern California blowing like this. And this is often difficult to see on a map like this because these models don't have the resolution to adequately resolve the complex topography of Southern California. But notice something interesting here is in this gap in topography, the winds are accelerated right downstream. So what you end up getting is essentially a literal wind tunnel effect where you have flow from the high desert right down to the coast like this. That's warming, it's drying, it's intensifying. So this is a classic Santa Ana event. And these wind speeds might not look that strong, but again, these are sustained wind speeds, and it's showing patches of 30 to 40 knots, so up to 45 miles an hour sustained. That's a big deal because the gusts will be stronger, and in general, the winds will be stronger than represented here because, again, this is not a model that can fully represent the complex topography of the region. So this is, in other words, a major Santa Ana wind event. It looks almost exactly what you'd expect it to look like, dynamically speaking, from a meteorological perspective. Classic Santa Ana wind event. There'll be high risk of fast-spreading wildfires in Southern California. Again, the winds in Northern California won't be quite as strong, and also the vegetation isn't quite as dry. Looking forward, right now, there's a bit of disagreement between the European model ensemble and the American model ensemble, the two major predictive tools. But if I step forward in time, we kind of see this repeating pattern again. So we go toward mid-November, another major Santa Ana signal. This is another inside slider, so this could be another major wind event in Southern California with more diffuse ridging. Maybe a bit of a change, but that still looks kind of like an inside slider, but maybe a slightly less inside slider again, going toward late November. That's suggesting that not a whole lot of water is likely to fall. In fact, the next 10 days look outside of the north coast and maybe the Shasta region nearly or completely dry across most of California. And even as we go out toward late November, there's a little bit wider range of possibilities, but it's still looking relatively dry. And a relatively similar picture from the American model ensemble, although it is a little bit wetter out beyond a week from now, but still really nothing indicated for Southern California, so it's likely that these inside sliders will continue to bring offshore wind events that raise the risk of wildfire into that period. But I just wanted to point out one thing about the vegetation moisture. Right now, this is an operational tool to see how dry things are, and these are color-coded. Apologies if you're colorblind. The default panel on the SCUI is red and green, but essentially most of California is green. Some of it's closer to yellow, but really what this is showing is that there's a gradient between northern and southern California. Everything north of about I-80 is about, I guess I'll draw on this map here again a little bit. Again, when I say I-80 corridor, I mean about here. So everything north of about this point in California, I'm not too concerned about wildfire risk in this period. Not because it won't be windy, but just because the vegetation is pretty dry. And that's reflected on this map. But as we get down into the Bay Area, it's a little bit more of a mixed picture. Things are drying out somewhat, especially in some locations south of San Francisco. So there are red flag warnings in effect here. There could be some public safety power shutoffs on election day, even. So that's an interesting combination I'm not sure we've seen before. Perhaps we have, I don't recall. But generally speaking, the places that are not dark green here are the places where there might be some wildfire risk, but it's still not very high. As you can see, that's still only in like the 60th percentile of flammability. This is an energy release component map. Energy release component, you can just think of it colloquially as an aggregate measure of vegetation flammability. Coastal Southern California, though, is drier, and the more important part is virtually everywhere you see that the upward arrows mean that the trend is towards drier. And this is what we expect to see throughout the week. I think this map will start showing orange and reds in Southern California, so in this region by Wednesday or Thursday. And that's why the major concern about wildfire risk is down here, with some risk up into here perhaps, but not super high. And really everybody about north of this line has not so much to worry about. Even though there are some red flag warnings that extend north, I still think it's a little bit marginal given the vegetation moisture. Doesn't mean the risk is zero, doesn't mean there can't be fires, but it does mean we're not in some super extreme territory. And I think that generally holds perhaps for this entire region. There's some risk towards the southern end of the box, maybe not a whole lot. But down here, it's an entirely different story, and this could be a major fire weather event. So I'm going to pause here, take a look at the questions that have come in. I think I've actually done, for once, a good job at doing this halfway through, because I want to talk about something completely different in the second half. So I'm going to take some questions, look at comments from the audience now before I do so. All right, so let's see what we've got here. Thanks for the kind words about the documentary. Again, I have included a link at the beginning of the comments, and I encourage everybody to check it out if they haven't already. Let's see here. Yep, there's the comment from up in Humboldt County where it's very wet. Yeah, fire season is over up there unless something very weird happens, which is not unusual by November. That's quite typical. That was an interesting question. I've never heard of an East Coast counterpart to the Santa Anas. What is the usual wind direction on the East Coast, or does it vary more? So what's interesting is the prevailing winds on both the West and East Coast are from west to east. Most of the time, winds blow, broadly speaking, from more west to east than they are east to west. There can be exceptions, of course, and sometimes it's southwest to northeast or northwest to southeast, but usually there's at least a west to east component on that compass rose. And that's true on the west coast and in the east coast. In fact, it's also true even in the southern hemisphere. Sometimes people get confused about this, but the direction of the wind currents is not something that is different in the northern hemisphere and the southern hemisphere when it comes to the westerly jets. So the prevailing westerlies exist in the middle latitudes of both hemispheres. If you're on the west coast of Australia, for example, or the west coast of South America, you are still getting primarily west to east winds in the middle latitudes. What changes is latitudinally, at different latitudes in the Arctic and in the tropics, you can get winds that primarily blow from east to west, although more weakly. So what matters more than which hemisphere you're in, and the Coriolis effect, is actually what latitude you're at within that hemisphere. So in general, in Europe and the US, west coast, east coast, doesn't matter. The wind is usually blowing from west to east. In all of these cases, it can blow from east to west, but it is far more unusual for it to do so. The reason why the East Coast doesn't get Santa Ana wind events, though, for the most part, is because the topography is completely different. The transverse ranges of Southern California are some of the steepest mountains in North America. They rise very quickly. Just think about the diversity of topography, for example, in LA County. If you go from the west side of LA to the top of the San Gabriels, I mean, that's an incredibly large transition. You go from literally being at sea level to being up at 10,000 feet in how many miles as the crow flies? There isn't any topography like that on the East Coast. And so it is a geographic difference that drives this primarily, more than a climatological one. Now, there are also climatological reasons why you tend not to get that on the East Coast as well. But it's primarily because you have this elevated plateau to the east of California, or really even within California, so the high deserts, and then the Great Basin to the east of that, separating a low elevation coastal area pretty abruptly. And you also tend to see storms that like to dive southward sometimes inland of the coast, those inside slider type systems. That's a little bit related to the geography too, in a slightly more complex way that I won't get into now. But generally speaking, it's the topography that allows it, because if you do get east to west winds in Southern California, they're inherently flowing down slope in elevation, and pretty steeply at that. And there really isn't anywhere on the East Coast where that can happen to the same extent. Now, there is downslope flow on the East Coast, but it is ironically west to east winds that are downslope, because of course, if the ocean is to the east, and any topography above sea levels to the west, technically that's downslope. So you have the Appalachian Mountains, primarily, on the East Coast, and you can get downslope flow in the Appalachians. In fact, the somewhat rarer but still extant wildfires that occur in the southern Appalachians often occur during such downslope wind events, for example, in the Carolinas, where wind blows from west to east, which there means that the eastern slopes, rather than the western slopes, are what get the downslope. So you can have downslope winds on any mountain range, essentially on the leeward side, or the opposite side of the mountain range, which the wind is hitting first. And here, along the Front Range in the Rocky Mountains, again, downslope warming winds are actually, again, west to east winds, because the Rockies are just to the west, and the elevation decreases as you go east. But in Southern California, the elevation decreases as you go west. And so fundamentally, that's why you get Santa Ana winds. Plus, it's the fact you just have such ridiculously tall mountains not that far from the coast and a giant elevated plateau only 100 miles inland. It's a good question, though. Okay, so that's most of the questions that I've got about California. I'll move on to Spain. Give me a moment here. So, and I don't have graphics to show right now. I didn't have time to pull those up for you for Spain, so you'll just see me talking. As many folks are probably aware, there was a really catastrophic flood event in the Valencia region of Spain last week, and which frankly remains ongoing. In fact, renewed very heavy rainfall occurred this week, but last week's rainfall was just truly extraordinary, where some places saw an amount of rainfall equivalent to their annual average in 3 to 6 hours. So anywhere in the world, that's going to cause problems. But importantly, these aren't super arid regions. That can happen in places like, for example, the Imperial Valley of California, where the average annual rainfall is only like 1 to 2 inches. And so if you get a really heavy thunderstorm downpour that drops 3 or 4 inches, that's a couple times your annual average in just an hour or so. But the math becomes harder in places that aren't quite so dry, and in a lot of Mediterranean Spain, typically receives anywhere from 25 to 40 inches of rain in a year. So yes, in some cases, there were places that saw something like 20 to 30 inches of rain in a day, in a single day. And although this part of Spain, it certainly isn't flat, it's also not nearly as mountainous as is coastal Southern California. And so it's actually harder to achieve these very extreme rainfall amounts. And so there were places that saw close to half a meter of rain. So again, a meter is somewhere between 3 and 4 feet of rain in just a 2-day period. So half of that is still just a phenomenal amount of water. And as always, local watersheds, rivers and creeks and streams, are adapted. Essentially, they exist as they do. They are a reflection of the intensity of precipitation that occurs in a particular place. So rivers in places that receive a huge amount of precipitation on average look like rivers that receive a lot of flow on a regular basis. Rivers in deserts are often ephemeral. They don't always have water flow, but they look like you'd expect to see with rivers that see flash flooding, so systems that have infrequent but very intense bursts of water. The river systems in this part of Spain are somewhat intermediate. It's not a deep desert, but it's also relatively Mediterranean, warm, dry, summer type regime. And so this is somewhat analogous to certain parts of California seeing their annual average rainfall in a day. In Southern California, and think about what it would mean, for example, if a wide swath of LA County saw its average annual rainfall, which, depending on where you are in the county, is from anywhere from the upper from about 10 inches in the deserts to 30 or 40 inches in some of the wettest spots in the mountains. So let's just call it 20 inches, which is true in some spots, 25 inches. Seeing that in a 24 to 36 hour period. It would be a catastrophe, right? Well, that's what happened in Valencia, near Valencia, and it really was just a phenomenal amount of water. And what happened was a little bit different than California's typical atmospheric river systems. There was an atmospheric river involved, but the main feature was a highly stationary cutoff low pressure system. And this is somewhat analogous to what sometimes happens in Southern California, where some of the most extreme rain and flood events were not always big-time Pacific atmospheric rivers, but are sometimes cutoff low pressure systems that stagnate for an extended period of time and drop a lot of water all intensely. But what happened in Spain was a little bit different because this was a highly convective event, meaning that it contained intense thunderstorms. In fact, there were tornadoes and large hail to go along with this extremely heavy rain. But it turns out that the Mediterranean basin in particular is especially the Western Mediterranean, is very good at flexing enormous amounts of water and energy into storm systems that drop just kind of incredible amounts of water and extremely intense thunderstorms in some parts of the Western and Northern Mediterranean. So think the east coast of Spain, Italy, France, so occasionally even into Greece. It's often said that California has a Mediterranean climate, but what it's often really meant by that is it has more of an Eastern Mediterranean climate. So thinking about Israel and Turkey, somewhat more so than the Western Mediterranean, because the Western Mediterranean does tend to see these very intense convective events. There is a localized tornado alley, for example, in Italy, and it's not uncommon to see large hail and waterspouts even in the summer months in some parts of the Mediterranean. Not all the time, but certainly more often than we do in coastal California. So it is a place that's susceptible to this because the Mediterranean, of course, is a very warm, mostly closed system. So it gets the water temperatures there are far warmer than the Pacific Ocean west of California. The air is often stable, but when there is a storm around, that super warm enclosed sea, which is now dramatically warmer than it used to be due to climate change, this year it's been running 5 to 6 degrees centigrade, meaning essentially 10 degrees Fahrenheit above the long-term average. So just really warm seawater can really contribute a lot of extra, not just moisture to the atmosphere, but in this context also atmospheric instability that increase the likelihood and the intensity of thunderstorms. And so what happened here was a somewhat regionally localized ban of training thunderstorms. Training is a term that refers to when these rain showers, which is a bit of an understatement, move over and over again over the same area, and they keep back building. So although they are moving forward, there's always more developing behind the first ones, and because of the axis of motion, the new storms that redevelop behind the old ones just keep moving over the same areas over and over and over again. And this was facilitated by this stagnant or cut-off low-pressure system. Something that I was not aware of until last week was that, and there was actually some mistaken news reporting initially, referring to this as Storm Dana, D-A-N-A. And in Europe, the meteorological agencies do name winter storms or non-tropical storms. We don't do that in the United States. The Weather Service does not name storms. They name hurricanes, tropical hurricanes only, but not other types of storms. In Europe, though, it is common practice now to name all storms. But interestingly, this was not actually a storm called Dana. It was an unnamed storm. But what a lot of news agencies were referring to as Dana is actually an acronym, probably more appropriately DANA, because it is a Spanish acronym. And it's an acronym that stands for, it's D-A-N-A, Depresión Aislada en Niveles Altos. So essentially translates to an isolated depression at high levels, I think. That's the pretty literal translation, but what it really means is cut off low. So it's an acronym, and I don't know, by the way, if this is a universally accepted acronym in Spanish. I don't know if meteorologists in Mexico would use this term. It may be a sort of an Iberian Spanish convention, meteorological convention, and I'm not quite attuned enough to that world to know. But in any case, it's interesting that there seems to be, by the way, this is a bit of an aside, it's interesting that there seems to be a very high population level recognition of this acronym. So if you were to refer to, in the United States, for example, the term would be a cutoff low pressure system. Well, the listeners today might be able to identify that because this is a bit of a rarefied group where there's more than the usual number of weather geeks. I would include myself in that in the audience. But it's interesting that in newspaper headlines and in social media posts, everyone's referring to the Dana, and I really was confused by this because I thought it was the storm name, but it turns out that there is a wide level of public recognition of the kinds of challenges that cut-off low-pressure systems can bring on the Iberian Peninsula, and Spain in particular, which is an interesting social and meteorological confluence that I wasn't aware of. Part of the reason for that, by the way, is that when there are systems like this, particularly in autumn and spring, it is widely known that they can cause big problems. And I think this is partly because when you get a stationary low-pressure system over or near such an incredibly warm body of water, that is a recipe for things to go kind of sideways. And that's what happened last week with just catastrophic flooding of the city of Valencia itself, as well as the surrounding province and other cities nearby. It's one of those situations where the initial lack of news was pretty bad news, and there was dramatic video of thousands and thousands of vehicles being washed into piles in downtown areas up to 3 stories tall. And there, unfortunately, sound like there are the death toll is likely in the hundreds. It's already confirmed to be in the low hundreds, but it's likely in the high hundreds. And some of that includes people who were trapped as much as 3 stories underground in parking garages at shopping malls. The water came so quickly that it filled up these 3-story underground parking structures in about 15 minutes before people were able to get out. So it's a pretty horrific situation. Again, this was a high velocity, high intensity flood in a highly populated, highly urbanized setting. A lot of people who were caught unaware were on the roads and in cars and on highways, even on freeways, like these divided interstates. And those roads were just completely overwhelmed. The bridges were washed away, overpasses collapsed, and even the largest vehicles became corks bobbing in the floodwater. So these really horrifying, dramatic images, not entirely unlike some of the images we saw coming out of western North Carolina a few weeks back with Hurricane Helene's aftermath on the record-shattering flooding there, although in some ways even more shocking because in this case these are much more heavily populated areas and these were not super mountainous regions. It's hilly, but the topography is much less extreme, and so it's even harder for water to be concentrated into such extreme velocity. And yet it still happened here because of these enormous volumes of water. So the proximal culprit is the Dana, this cutoff low pressure system, and the fact that the water of the western Mediterranean and of the northeastern Atlantic, where some of the source moisture came, was far warmer than average, so the unusually warm oceans. The question has been, of course, is there a climate change connection? And I think the answer is unequivocally yes, there is. The exact magnitude of it is something that's not always easy to ascertain at first glance, but I'll let you know how I think about these sorts of things. On average, as I've said over and over again, what we're seeing is this expanding atmospheric sponge effect in a warming climate, meaning that the atmosphere's ability to hold water vapor increases exponentially at about 7% per degree centigrade or 3 or 4% per degree Fahrenheit of warming. That's true globally and locally, and this is a part of the world and an ocean basin that has warmed faster than the global average, so perhaps globally we're seeing a year 1.5 degrees centigrade or so above the long-term mean, but locally the numbers can be even greater, maybe more like 2+ degrees centigrade of warming of the long-term mean. That gets us to 10+% increase in the potential precipitation intensity right off the bat. But we also know that there are certain situations where you might actually see an amplified effect of climate change on extreme precipitation events, and those would be in particular events that include vast, unusually warm ocean water sources and or high-intensity convective extremes. In other words, thunderstorm downpours. And we check both of those boxes in this case. And so arguably, the studies have shown that the rate of climate change contribution to events like that can be up to double that you'd expect just from that increase in the atmospheric sponge. So rather than 7% per degree centigrade scaling, it might actually be closer to 10 to 14% per degree centigrade. Okay, so now all of a sudden we're talking about not just a 10% increase in the magnitude of the event, but maybe more like a 20+% increase. And then when we're talking about rainfall on the order of 20 to 30 inches in a day, you take 20 to 30% of that, and that's not a small number at all. That would be a heavy and maybe even flooding rain event in its own right on top of what was already going to occur. So when we talk about these things also, it's important to realize that, say it was only 10%, let's be very conservative and say that climate change only made the magnitude of this event in terms of the precipitation that fell 10% more intense. That still means that the event as it occurred, the likelihood of seeing an event of the magnitude that was actually observed is probably at least 100% higher than it was historically. Often a 10% increase in magnitude yields about a 100% increase or a doubling in the likelihood of seeing an event of that extreme magnitude in the first place. That's just how the statistics work when you're out in the upper tail of a heavy-tailed distribution like that. Similarly, a 20% increase likely means there's a bit like a 200 to 300% increase. So that's sort of the scaling we tend to see. But the other thing is, again, just going back to that 10% increase in the magnitude conservatively in the amount of rain that fell on an event like this, it does not mean the impacts are 10% worse. It's highly likely that the impacts are far greater than 10% worse than that 10% increase in the magnitude of the precipitation event would suggest. Because when it comes to a flood event, or really any other natural hazard that becomes and cascades into a disaster, there's all sorts of thresholds involved. And with a flood, it's fairly easy to visualize. If there's a flood control system in an urban area, the water is fully contained in that system up to a certain point. Whatever that point is, however, whatever the values are, you add 10% to that point. If you're right up at bankful and you add another 10%, you're in a world of trouble, because now instead of having this high velocity water shooting down these concrete river channels in urban areas, but staying contained within the channel and flushing rapidly out to the ocean, there are some challenges with that, but at least it prevents the city from flooding. Now, if you're 10% above that bankful, now all of a sudden that last 10% of the water is shooting at high velocity into highly populated areas, washing cars into the creek, washing debris into the creek, into the streams, into the rivers, and then using that debris as battering rams to bring down bridges and collapse retaining walls and compromise that flood control infrastructure, which is just what happened here. So all of a sudden, that 10% of flow above the top of these thresholds, above these barriers, is itself quite dangerous and destructive, but then it starts to have this self-reinforcing feedback where it actually becomes even more damaging, because by virtue of being above that threshold, you start to compromise the ability of the system itself. And then once it's compromised, then it isn't offering the same level of protection. So if the event continues, now it's as if you didn't have a functioning flood control system in the first place because you got that extra 10%. So there are cascading impacts, and this is true in so many contexts, where people say, is a 10% increase in the precipitation intensity really all that big of a deal? And I would say, yes, it is. First of all, it might not only have been 10%, it might have been more like 20% if it's a super Clausius-Clapeyron accelerated precipitation downpour, thunderstorm downpour situation. But even assuming it is only, say, 10%, that can result in consequentially different impacts. We saw this with the Oroville Dam crisis, which it's believed that climate change increased the inflow into Oroville Dam by 10 to 20% in that event relative to what it would have been historically. And we almost had a catastrophe, but it was averted. It was a dam crisis and not a dam catastrophe. The emergency spillway and the auxiliary structure ultimately did not fail, sending a 30 or 40 foot wall of water downstream into the Central Valley, fortunately, in that instance. But what if it had been 10 or 20% higher, as it would be with another 10 to 30 years of global warming? Would we still have been in crisis mode, or would it actually have become a catastrophe? There's reason to believe that the outcome could have been much worse, and that's precisely, again, because there is a threshold in that kind of system that matters. The amount matters. You can't just say that because climate change made an event 10% wetter, that the impacts are 10% worse. In a lot of cases, it's not linear, and you see a much larger scaling of impacts than you do from the physical hazard event magnitude itself. The same thing is largely going to be true with things like extreme wildfires and extreme droughts, for the similar reasons. So, and for hurricanes, by the way, because a 10% intensification of the wind speed, again, the damages from hurricanes increase on a quadratic scale. So you increase the magnitude of the wind by 10%, you're increasing the actual hazard, the damage from that wind, using an exponent on that 10%. So it's not as simple as 10% increase in intensity, 10% increase in damage, 10% increase in harm caused. This is a very classic example of why usually the scaling is a lot higher. So that's the broader context for what happened in Spain. It's eerily similar, even though, of course, in North Carolina, it was the result of a landfalling hurricane, which made it inland. That was Helene. It's the same basic idea. Record-breaking amounts of moisture in the atmosphere, coinciding with atmospheric instability in some mountains to squeeze it out. A little bit less so in this case, but similar situation, resulting in catastrophic floods and just mind-boggling rain totals, just vastly exceeding what you would experience usually even in a very wet month in a given place, and doing so only in a day, and in some cases exceeding the annual average rainfall in one day in a region that's not an arid desert. And we've seen that now over and over again. We've seen that earlier this year in Central Europe. We saw it several years ago in Germany. We've seen it in southeastern Australia. We've seen it with Hurricane Helene in the Carolinas. We've seen it in the Sahel in Africa this year as well. We've seen it in at least 4 different places in China in the past 5 years. We've seen it in India twice. We've seen it in Pakistan as well with the catastrophic floods there. We just keep seeing this over and over and over again. And that, folks ask, is it because we're paying more attention than we used to? Is there more smartphone video footage of these car soup events where these thousands of vehicles get washed into drifts, like snow drifts at the bottom of these hills? And the answer is we are, of course, seeing more of it because 20 years ago, not everybody was carrying around a high-definition video camera that could be live streamed to the world. So, sure, there's more documentation of what happens than there used to be, but there is something else going on here. We are seeing an intensification of these very extreme precipitation events, and that is being caused by our warming world and our warming oceans. So, the answer is yes and yes. And if we assume it's only one or the other, then we might be doing ourselves a major disservice. But personally and professionally, it is kind of disconcerting to continue to see these episodes of conspicuously, it's almost in the uncanny valley, if you will, just to see some of the imagery of large objects being moved by water that shouldn't be, in settings where it shouldn't be happening. In this moment of AI and fake videos circulating on the internet, I think it's going to get difficult to differentiate sometimes, and I think that might make folks a little bit disbelieving about the extremity of some of these events when they actually do occur at this super extreme level, like this one. There's still some tells, by the way. Interestingly, AI does not get water flow right or fire right, so it seems to have a real problem with fluid dynamics still. We can have another conversation about that later. It's something that gets to me every time. The new Hollywood special effects, they all look much faker than they did 20 years ago if you have an eye trained towards fluid flows. But anyway, that's a conversation for another day. But the point is this: Spain is just the most recent region to see this kind of extreme event, and we don't hear about them as often when they happen in some places. There have been equivalently extreme events in the Sahel, the African Sahel this summer, and we didn't hear about them as much because there aren't as many smartphones around, and there is less global news focus generally on the global south. So there is, sometimes we actually hear less about these events perhaps than is justified given their extreme intensity. But we focus on the ones that have this visceral footage, partly because that's what gets people's attention, because you can actually see what happened in real time in a way that's not always the case everywhere else. But it certainly isn't the only place that's happened. Even just in the last 3 or 4 months, I can count maybe 4 different events of this magnitude in as many months. And that is pretty alarming. Again, this is a year around 1.5 degrees centigrade of warming. Not in the long run. We're still below it in terms of temperature targets. We're still around 1.3, 1.4 long-term average. But we are getting a taste of 1.5 right now. And it looks kind of ugly. And fortunately, California hasn't had to deal with extreme floods of this magnitude yet. There's been flooding in recent years, but it has been nowhere near the magnitude of the events we're talking about in this setting. I hope that continues, but professionally, to be quite honest, I don't think it will continue forever. Eventually, California will see its event. It will see its arc storm, if you will, equivalent level event. And we have seen arc storm level events now in multiple places in the world just in the past 4 months. This was in Spain, in Valencia region, this was an equivalent smaller scale version of that. Western North Carolina was perhaps a slightly larger scale version of an event of that kind of magnitude that we're talking about here. So when folks say that California's flood control systems and water systems weathered the recent floods quite well, I mean, I'm glad that they did. It's certainly better than the alternative. But on the other hand, those were nowhere near as big a test as an event of an equivalent severity of seeing, for example, a year's worth of rainfall in a day, as occurred in Spain, or seeing what are estimated to be the equivalent of multi-hundred-year recurrence intervals for very extreme rainfall in Hurricane Helene, which, again, we can quibble about the details of those return intervals, but still, it's very clear that it was greatly in exceedance of anything that had been observed in the past century. And that's probably not a coincidence. Okay, folks, I think that just about wraps us up for the day, right on the hour. Thanks for joining again. Please do check out the documentary. It's linked in the chat, and I'll add a link to the full video after the fact. And if you're in Southern California, Wednesday, Thursday will be big deal fire risk days due to strong Santa Ana winds and very dry vegetation. Some risk further north, but significantly mitigated by the rain that's recently fallen up in Northern California. So I am not super concerned about the northern half of the state, but coastal Southern California is a whole different story. Watch out there. I'll definitely be following this week. And if you haven't done so yet, go vote. Tomorrow's the election.